In this web lecture, I'm going to explain how to correctly read and interpret a phylogenetic tree, how to understand the evolutionary story that a phylogenetic tree is telling, and also how to determine whether two trees that look very, very different are actually the same tree, or if they represent a different evolutionary hypothesis. To review from the previous web lecture in this series, these branching phylogenetic tree diagrams represent an ancestral species that underwent a speciation event. One species split to become two separate species, and each branch represents a descendant species. In fact, if we had complete information, we could represent the entire evolutionary history of life on Earth and all of organismal diversity as a branching series of speciation events that happened at different places in different times throughout the world and throughout history. So this is what every phylogeny that you ever see means. This is how we interpret it. An ancestral species undergoing speciation to give rise to two descendant species. And we can represent these branching patterns in a number of different ways, and you'll see different phylogenetic trees that look like any of the following. You can see these block patterns with the root at the bottom going up toward the tips at the top. We can have it in block form but going left to right, so we've got the root at the left and the tips at the right. Or vertically as sort of V branches, turning this representation on its side. So again, root at the bottom, tips at the top, and remember the time scale always goes from the root to the tip. So in this case, it's going from the bottom to the top. In this case, it's going from left to right. And in this case, again, it's going from bottom to top because the root is at the bottom, tips are at the top. Because these nodes and branches represent speciation events, the two branches are completely symmetrical. What I mean by that is if we look at this node, where we have green fish splitting from blue fish, it doesn't matter whether green fish is on top or on bottom, whether blue fish is on top or on bottom. This is just one species splitting into two. So if we look at this on our phylogenetic tree representation of this clade, that means that we can rotate around any node because every node is just a speciation event and it doesn't matter which species you put on which side. So this phylogeny means exactly the same thing as this phylogeny with blue fish now on the left and green fish on the right. If we even look at deeper nodes, so this earlier node, we can rotate around that node too and have blue fish and green fish now on the left and white fish on the right. And they both represent identical evolutionary hypotheses. A common ancestor splitting into two descendants, and the representation of which is on which side makes no difference whatsoever. So we can also do this on more complicated phylogenetic trees. So the one we're looking at now is a phylogenetic tree for the vertebrates. And this is the way we typically see it, right, with what we think of as more ancestral species over on the left, working our way up to more and more complex species till we reach the pinnacle over here of mammals, but it doesn't have to be that way. So if we look at this node here, a very simple one, crocodiles and birds, we can switch that around and now have birds on the left and crocodiles on the right. We may think of birds as being more highly evolved or more derived, but that does not mean that it has to be further to the right on this phylogenetic tree. Those can be switched around and it means exactly the same thing. We can look at deeper nodes, so now if we look at birds plus crocodilians plus snakes and lizards, we can rotate around that one. And now we have snakes and lizards here on the inside, birds and crocodilians. Maybe you don't think mammals are so great, they don't deserve to be way out at the other side. Maybe you like turtles. We can do that. We just switch around that node, and now we've got turtles up here at the tippy top and mammals kind of buried within. Maybe you really like sharks. Sharks are your thing. You think they deserve to be way out here in the place of honor on the right. We can do that too. All of these phylogenetic tree representations are identical. So how do we know whether two trees that look different are actually identical or equivalent trees or whether they actually do represent different phylogenetic relationships, different hypotheses about the evolutionary relationships between the groups. The key to understanding that is understanding this concept called sister taxa. Sister taxa are groups of species on the tree that both come from the same node. So each node defines one pair of sister taxa. So if you look at the region, the two branches right adjacent to the node, one branch comes off this way, one branch comes off this way. Everything that comes from this branch is one sister taxon, and everything that comes from this other branch is the other sister taxon. So hagfish on one side and everything else on the tree on the other side, because everything arises from this little branch. Another example, so if we look at this node, this is going to define a pair of sister taxa, one coming from each branch. So in this case, we've got Actinopterygii, or the ray-finned fish, on one side, and everything else on the tree on the other side, because all of this arises from this branch coming from the node. Everything branches off of this one. Further up, if we look at this node here, snakes and lizards on one side, birds plus crocodiles on the other side. So snakes and lizards is one sister taxon. Birds plus crocodilians is the other sister taxon from that node. So now if we want to know if two phylogenies are the same, we've got a couple of choices to determine that. One, we know that if you can get the other tree by simply rotating a node, that those are equivalent. So you could go through the whole tree just rotating nodes and seeing if you get the other tree. But if you're talking about a big complicated phylogeny, this is very time consuming and it gets very confusing. So an easier way is to go node by node and compare groups of sister taxa. If each node defines the same pair of sister taxa, regardless of the order, the trees are equivalent. So if we look at this one, a very simple example, start with this node and we can see that one sister taxon is A, the other one is B plus C. And on this tree, one sister taxon is B, the other one is A plus C. They're not identical groups of sister taxa, so we would say that these are not equivalent trees. Another thing that does not change the evolutionary hypothesis portrayed in the phylogeny is removing nodes and species. In fact, you've never ever seen a phylogeny that does not have species and nodes removed from it compared to what exists in the world. So just because a species is missing from a phylogeny or a node is missing from a phylogeny does not necessarily make that phylogeny wrong or different from a similar phylogeny. And to convince yourself whether these two phylogenies are equivalent, we can go through and do just what we just described, compare groups of sister taxa. So this phylogeny on the right compared to the one on the left has nodes 2 and 6 removed. It also has rotated node 5. So we can just go through node by node, comparing the nodes that are present just on this one, right, because it's missing nodes compared to the other one. So we'll start with node 1, and we see that on the phylogeny on the right, that node results in one sister taxon that consists of the Canada lynx, and another one that consists of snow leopard, tiger, leopard, and jaguar. On the phylogeny on the left, we can see that that same node divides between Canada lynx on one sister group and snow leopard, tiger, leopard, and jaguar on the other side. Again, the order doesn't matter as we're going node by node. We just want to make sure that the same groups are included in the same groups of sister taxa. So going to node 3, on the right, that separates snow leopard from tiger, leopard, and jaguar. And on the one on the left, again, it separates snow leopard from tiger, leopard, and jaguar. Node 4 separates tiger from leopard and jaguar on the right and also on the left. So we can see that these are completely equivalent phylogenies with some species removed and one node rotated. So it just depends on what relationships you're interested in thinking about, what species and nodes are represented in your phylogeny. You do not have to represent the entire group to be able to work with these phylogenies and understand the evolutionary relationships between groups and the evolutionary events that occurred. So let's finish up by talking about how evolutionary novelties or evolutionary events are represented on phylogenetic trees. And to do that, we're going to continue with this example of green and white and blue fish, but with some different assumptions in our model. So in this case, we're going to start with a population of green fish that underwent a speciation event. And on this line, there was a mutation that led to white fish. So white fish evolved from green fish ancestors. In both lineages, there was an additional mutation that led to blue fish. So in this case, green fish split into green fish on one side and blue fish on the other side. There was a split here that led to two different species of white fish. They're different in some other way besides color. So we've got one species that continues on as white fish, one that undergoes another speciation event. One had a mutation that led it to express blue and became a species of blue fish, and then the other group retained the ancestral condition of being white. So remember that we said that characters that are shared derived characters within a clade are called synapomorphies. So we mark synapomorphies on a phylogeny with a little line crossing the branch somewhere between the ancestral condition that had the ancestral state and the group in which that state evolved. So here we've got an evolutionary event or an evolutionary novelty. There was a mutation here that caused this group to go from green to white. We've got a mutation here that allowed blue to be expressed, and a mutation here that went from green to blue. So white is a synapomorphy of this group that defines this taxon. So let's think again about the terminology and the fact that when we're thinking about plesiomorphic or ancestral states versus apomorphic or derived states of characters, they always have to be thought about with respect to a particular clade that you're talking about. So let's go through some examples. So if we think about this entire clade defined by node 1 here, we can say that the plesiomorphic state is green. Why? Because the common ancestor of both of these branches were green fish. We can see it right here. This common ancestor was green. White happened somewhere along this line. So that's an apomorphic state within this clade. There was an evolutionary event that happened within this clade. The entire clade that we're referring to, defined by node 1. And blue is an evolutionary event that happened twice within this clade. So white and blue are both apomorphic states with respect to clade 1. If we look at the clade defined by node 2, so that's just these three groups, we have a different situation. So now in this case, we've got a synapomorphy that joins all of them together, which is white. That was something that happened in the common ancestor of all of those. So we call white a synapomorphy of this entire clade. But actually the plesiomorphic state for this clade is white. Why? Because the common ancestor of all of these species was a white fish. So the plesiomorphic state is white, and we have an apomorphic state with respect to this clade, which is blue. This is something new that happened, an evolutionary change that happened within this clade of white fish. Thinking about the clade defined by node 3 here, the plesiomorphic state continues to be green. This common ancestor was green. This common ancestor was green. We can see it right here on this diagram. So the character state that was possessed by the common ancestor of the clade is the plesiomorphic state. The apomorphic state that's derived within this clade is blue. So blue is an apomorphic state with respect to clade 3, and green is the plesiomorphic state. Now if we look at clade 4, defined by this node, node 4, the plesiomorphic state continues to be white, right? This common ancestor was white, this common ancestor was white. So whatever the state of the common ancestor of that group, that is the plesiomorphic state for that clade. So just this clade that includes bluefish and whitefish. And the apomorphic state, again, because it's the result of an evolutionary event that happened within that clade, is blue. So to review this within the vertebrate phylogeny, we can look at a feature such as the cleidoic egg, or the shelled egg, that we see in many of the terrestrial vertebrates. And so that evolved somewhere after this group called the amniotes split off from the amphibians. So the cleidoic egg is a synapomorphy of the amniotes. It is an evolutionarily derived feature that was inherited in common by all of the groups of amniotes. So we can say with respect to all of the land vertebrates, the tetrapods, the plesiomorphic state is not having a shelled egg, and the apomorphic state is having a cleidoic egg. If we look within just this group of amniotes, the plesiomorphic state is to have a shelled egg, a shelled cleidoic egg. Why? Because that was the state of the common ancestor of all of the amniotes. So we say that when we have an evolutionary event like that, that's a feature that's going to be possessed by all of the descendants of that ancestor. That's what a synapomorphy means. But I'm a mammal. Personally, I've never laid an egg. So what happened? Somewhere along the line to mammals, we have the loss of the shelled egg. Okay, and we know that this is another evolutionary event, that it was lost because mammals share a lot of features in common with the rest of the amniotes, including the retention of the fetal membranes that you find within the shelled egg. So we know that this was a loss of the cleidoic egg and that mammals are actually part of this group. So, with respect to the group of amniotes, starting at this node, the cleidoic shelled egg is the plesiomorphic state. The loss of cleidoic egg is the apomorphic state. But the loss of the cleidoic egg is a synapomorphy that joins all of the mammals together. In summary, what I hope you've learned from this lesson is first that evolutionary trees or phylogenies are diagrammatic representations of historical speciation events and the origin of novel traits. So different evolutionary events can be mapped onto these phylogenies to show where on the phylogeny that evolutionary event occurred. And so in this way, we can read evolutionary trees or phylogenies as a story about evolutionary history, about speciation events and evolutionary novelties, new evolutionary events. Each node represents a common ancestor species that lived at some point in the past. The two branches represent a speciation event in that ancestral species. So one ancestral species splits to become two descendant species. Rotating the branches around the node does not change the evolutionary hypothesis represented by the tree. So each sister taxon includes everything that arises from that branch. And to determine whether phylogenies are equivalent, compare the sister taxa at each node through the tree. If each node defines the same pairs throughout the entire tree, the two trees are representing the same evolutionary hypothesis. A line through a branch indicates a new trait that evolved sometime between the speciation event below it and the one above it. So that localizes these evolutionary events at a particular point in time.